Hello everyone, I'm Zhang. I'm a Mercury postdoctoral fellow at the University of Galway, Ireland. Today I want to introduce the research of my Mercury project, which is about hard magnetic soft elastic metamaterials for tunable wave manipulation. I aim to understand the physical mechanism that enables transformable microstructure for metamaterial design, and I seek to find its application for wave manipulation. Magnetic soft materials is a composite consisting of magnetic particles embedded in a soft matrix, as this SEM image shows. Under the application of an external magnetic field, these particles interact with the external magnetic field, resulting in the overall deformation of the materials. According to the magnetic behavior of the particles, the composite can be divided into two classes, the soft magnetic one and the hard magnetic one. As shown by this schematic plot, the hysteresis effect of the soft magnetic materials is not obvious, which means they don't have magnetization once their external magnetic field is removed. By contrast, the hysteresis effect for the hard magnetic materials is relatively strong. That means they can have remnant magnetization without external magnetic field. Imagine the permanent magnet. Here my research is focused on the hard magnetic materials. The theoretical study of such materials originated in the 1960s when the foundation of magnetoelasticity and the mathematically analogous electroelasticity was established. Since then, the magnetoelastic theory has been further developed by researchers, as these examples show. More recently, driven by the material fabrication that enables programming of the intricate magnetization patterns in these materials, the research area has been witnessing explosive growth. The potential applications of such materials include biomedical devices, soft-bodied robotics, and shapomorphism. Here, my research interest is to integrate the unique transformative ability of hard magnetic materials into metamaterial design to achieve novel soft magnetoactive metamaterials for tunable wave manipulations. This includes the tunability of Bragg scattering bandgap, local resonant bandgap, elastic cloaking, as well as the tunability of nonlinear waves, the soliton. Okay, first let's see the tunability of Bragg scattering bandgap in the magnetoactive laminate system. The studied laminate system is made of two hard magnetic active elastomers with remnant magnetizations. Let's consider that an external magnetic field is applied in the same direction as the magnetization directions. Both of them are in the laminate direction that is perpendicular to the layers. In this case, the laminate will be stretched or compressed, and this will finally change the wave dynamics in the periodic system. Generally, for the hard magnetic materials, the intensity of the actuating magnetic field is relatively small. That means, for simplicity, we can assume that the magnetic behavior is linear. Here, Br is the remnant magnetic induction, Mr is the corresponding remnant magnetization. Mu0 is the permeability of vacuum and mu-r is the relative permeability of the material. Mu-r larger than 1 means that the material will be further magnetized under external magnetic field. With such assumption, the total magnetization can be expressed here, and the Lagrangian augmented energy density function can be written as follows. There are two terms, the magnetic part and the elastic part and the magnetic part. Using the energy density function, we can obtain the total Cauchy stress. Now we consider the boundary conditions. First one is the continuity conditions at the interface between the layers. The second one is the mechanical traction-free boundary condition. Since here we didn't apply any mechanical loads, the average Cauchy stress in the laminate system equals the Maxwell stress in the vacuum surrounding the laminate. Considering specific energy density function characterizing the purely mechanical response of the constitutive material, we can obtain the range of the laminate system for specified magnetic induction. For example, by controlling the magnetization distribution in the laminate, including the direction and the magnitude, the laminate can be compressed or stretched under external magnetic field. Okay, the laminate has been deformed under external magnetic field. Now we consider incremental motion superimposed on the deformed state. Using the incremental magnetoelastic moduli obtained through the augmented energy density function, we can finally obtain the equation of motion for the incremental waves as shown here. Then, by applying the Bloch wave theorem, we can obtain the dispersion relations for the incremental waves. Here, we focus on the transverse wave. This is the original band structure diagram for the system without external magnetic field. Here, the highlighted areas are the backscattering band gaps. Band gaps means that plane waves with frequency located in this range cannot propagate in the laminate system. As can be seen here, both the bandwidth and frequency precision of these backscattering band gaps can be tuned under external magnetic field. Okay, next, let's see the magnetic tunability of local resonant band gap. Compared to the backscattering band gap, whose operating frequency is determined by the lattice constant, local resonant band gap has the advantage of achieving stop wavelength with attenuation. Consider the local resonant metamaterial system shown here. The mass core of the local resonator is made of hard magnetic materials, with remnant magnetization shown by the black arrow. Consider that an external magnetic field is applied, such as in the horizontal direction. Magnetic body torques act on the particles which will rotate the mass core. As shown by this finite element simulation, as we increasing the intensity of the applied magnetic field, the rotation angle of the mass core increases correspondingly. Then, at a critical point, snap-through behavior is observed. To quantitatively characterize the magnetomechanical behavior of the local resonance system, we calculate the rotation angle of the mass core, the relationship between the rotation angle of the mass core and the intensity of the applied magnetic field. As shown here, when we apply magnetic field in the positive x direction, the curved beams will be compressed. Then, at a critical point, the snap-through behavior is observed. After that, if we reduce the intensity of the magnetic field gradually to zero, the system will be stable at its second stable state. By contrast, when we apply magnetic field in the negative x direction, the beams will be stretched. In this case, the system is monostable. For the considered local resonant state, the local resonant metamaterials, the unit cell has a local resonant state, and this is first natural frequency. When we apply magnetic field in the positive x direction, the curved beams will be compressed. Its stiffness reduces, and correspondingly, the natural frequency reduces. By contrast, when we apply magnetic field in the negative direction, the curved beams will be stretched, its stiffness increases, and therefore the natural frequency increases correspondingly. In this manner, we can tune the local resonant bandgap. This is the bandgap originating from local resonant effect, as seen here. Both the width and the frequency position of the local resonant bandgap can be continually tuned under an external magnetic field. Okay, next let's see how to achieve elastic cloaking using magnetomechanical coupling of hard magnetic materials. This is the so-called transformation method that enables cloaking, which means an object is completely invisible from its surrounding. To achieve such an cloaking, the core idea is to design the cloak material, which is also called transformed media. This can be achieved by applying a geometric transformation that enlarge a point in the background and map it onto the cloak inner boundary. Through this process, the material parameters in the cloak media will be revealed by the transformed governing equation. For example, let's consider that the background media is isotropic. The constitutive relation of the cloak media will be as follows. Generally, as can be seen here, since these two components are not equal to each other, the elasticity tensor of the transformed media will no longer exhibit minor symmetry. That's why we call the transformed media is asymmetric. To achieve such an asymmetric media, the core idea revolves around applying a carefully engineered distribution of body torque to modify the balance of angular momentum. Potentially, the necessary body torque can be achieved by utilizing the grounded torsional springs as shown here. An alternative approach can utilize the rotational resonance effect. However, such elastic cloak operates at a single rotational resonant frequency only and may not be applied to the static case. As shown above, since body torque is easily obtained in hard magnetic materials, can we exploit it to achieve elastic cloaking? Okay, let's consider that the cloak media is made of the mass spring model shown here. Here, the rectangulars or the mass blocks made of hard magnetic materials, and the bars connecting the mass blocks represent linear spring. The mass core has the remnant magnetization M, and let's consider that an external magnetic field is applied in the same direction as the magnetization direction. Then, when the lattice is deformed and the mass core rotates under an external mechanical loading, restoring body torque will act on the mass core. Such body torque is what we need to break asymmetric. Okay, first let's examine the effective elasticity tensor of the mass spring model. Consider that the lattice is subjected to a uniform displacement gradient, and all the mass blocks experience a rotation of angle phi. The total potential energy is composed of three terms. The first term is the mechanical potential energy stored in springs alpha. The second term is the mechanical potential energy stored in spring beta. And the last term is the magnetic potential energy that accounts for magnetomechanical coupling. By using the principle of minimal potential energy, we can express the rotation angle using the displacement gradient. Then, the effective elasticity tensor of the model of the lattice system can be obtained using Hooke's law, as given here. Recalling the required material parameters of the cloak media given by transformation method, we can determine the geometric and stiffness parameters that fulfill the transformation method. For example, this is the required parameters for the case that lambda equals mu. Okay, till now, the above analysis is based on the mass spring model. Now, let's consider the realistic microstructure model that corresponding to the ideal mass spring model. In the microstructure model, the rhomboid beams act as springs, and the hinge contact are jointed using a semicircle with a very small radius. Then, the last step in designing the lattice cloak is to optimize the geometric parameters of the rhomboid beam for the required stiffness parameters alpha and beta. For given cloak inner and outer radius and the number of layers, the geometric parameters for the microstructure located in each layer can be determined as shown in this table. Okay, first of all, let's examine the effective elasticity tensor of the microstructure in each layer. The numerically characterized the numerical homogenized effective parameters are shown by the solid stepped lines, which agree very well with the analytical solution shown by the dashed lines that are given by transformation methods. Okay, then the performance of the lattice cloak is examined using finite element simulation in console. Note that to save computational cost, here we consider the half cloak model. And in the simulation, the bottom of the system is fixed and an external and uniform displacement load is applied to its top boundary. We record the response of the system under different intensity of magnetic field, and for each case, the total displacement profile at the white dashed line is measured, as presented here. As can be seen here, as the increasing of the external magnetic field, the response of the system with the lattice cloak approaches that of the system with the ideal cloak. In particular, when the intensity of magnetic field is large enough, the performance of the lattice cloak matches well with the performance of the ideal cloak. Both of them effectively make the void invisible from the background. Okay, lastly, I want to show you the tunability of the soliton. Solitary wave was firstly observed by the engineer Zhang about 200 years ago. This is the experimental illustration of solitary wave in a very long water tank. As can be seen here, the excited water pulse is propagating stably without distortion or splitting. As we know, water wave is dispersive. What does dispersive mean? In a linear dispersive system, consider a wave pulse consisting of multiple frequency components. Since the system is dispersive, that means for different frequencies, the plane wave has different phase velocity. Therefore, the excited wave pulse will be distorted during propagation. This can be understood by considering that there is a group of people standing together. Then they start to walk toward the same direction. Since they have different velocity, After a time interval, they will be splitting from each other. However, as shown in the previous slide, the excited water wave path is stable during propagation, even though the water wave is dispersive. That is because here nonlinearity is considered. So, by introducing nonlinearity into a dispersive system, we can achieve stable wave propagation, such as the solitary wave introduced here. And previous study has shown that soft metamaterial systems, such as the classic auxetic metamaterial system consisting of rotating squares connected via thin hinges, can support the propagation of elastic solitons. Here, our idea is to introduce magneto-mechanical coupling into the purely mechanical system. In this manner, the microstructure of the system can be changed under external magnetic field, and we believe that this will finally change the solitary wave behavior of the system. Look at the system, we can see that deformation will be highly localized at the thin hinge, and the hinge deformation can be modeled by using a combination of three springs, including the longitudinal, shearing, and torsional spring. And the stiffnesses of these springs can be determined by using finite element simulations of the corresponding hinge model. In theoretical analysis, first of all, we need to express the deformation in these springs using the degree of freedom of the square unit, which includes two translational components and one rotational component. The total potential energy of the system will be composed of three parts. The first part is the elastic potential energy stored at the soft hinge. There are three terms corresponding to the three linear springs, respectively. The second part is the magnetic potential energy that accounts for the interaction between neighboring mass cores. The last term is the magnetic potential energy that accounts for the interaction between a single magnetic core and the external magnetic field. Using the total potential energy, we can calculate the deformation of the system for given magnetic fields. To examine the theoretical analysis framework, we perform finite element simulation directly in console, as shown here. All the square units rotate under external magnetic field, and when the direction of the magnetic field is reversed, the rotating direction of the square reverses correspondingly. The comparison between analytical prediction and finite element simulation is presented here. The left plot is for the macro stream. In finite element simulation, the strain is measured by comparing the displacement between two target points, as is shown here. And in the red plot is for the rotating angle of the square unit. We can see that our theoretical method works very well. We also did the comparison for other geometric parameters. In each case, the analytical predictions agree very well with the finite element simulations. Okay, now we investigate the superimposed motion on the deformed system induced by an external magnetic field. Each unit cell has 3 degrees of freedom. Correspondingly, there are three equations. These discrete equations can be solved numerically only. To gain more insight into the solitary wave behavior of the system, we need to establish the continuum model. This can be done by introducing 3 continuous displacement functions. In this manner, the displacement of neighboring units can be expressed using the Taylor's expansion of this continuous function. Then we found that the two translational displacement components can be expressed using the rotational displacement component. Finally, we obtained the continual model, the KG equation, which has solitary solution depending on the coefficient C1, C2, C3. Okay, to examine the continual model, we solve the initial discrete equation of motion directly using numerical tools in MATLAB. In numerical simulation, the model consists of 100 by 60 units, and the analytical predicted solitary solution is applied as input to the left boundary. To eliminate boundary effect, we apply perfect match layers on the top and the bottom boundary, and the distribution of damping coefficient is illustrated here. As shown by the numerical simulation, the excited wave pulse is propagating stably without distortion. The comparison between analytical prediction and numerical simulation is shown here. The upper panel is for the rotational movement, and the bottom panel is for the translational displacement component. In each plot, we present the displacement profile at 3 moments. We can see that in each case, the analytical prediction given by the continual model matches well with the numerical simulation. More importantly, by changing the direction and the magnitude of the external magnetic field, we can change the amplitude of the solitary wave. Okay, in addition to the rotating square metamaterial system, we also investigated solitary wave in origami-inspired magnetoactive metamaterial system. As shown here, the unit cell structure of the system consists of 2 plates and 12 beams. More importantly, the beam and the plate are connected via a highly deformable hinge that is made of very soft materials. Experimentally, the whole unit cell structure can be fabricated using multi-material 3D printing technique. Since the hinge is very soft, deformation will be highly localized at the hinge, and the hinge deformation can be decomposed into 3 modes. The first one is the out-of-plane rotation of the beam. The second one is the in-plane rotation of the beam. And the last term is the tensile deformation along the beam. In this manner, the total mechanical potential energy can be written as shown here. And there are 3 parts corresponding to the 3 deformation modes respectively. To examine the analytical model, we fabricate the unit cell structure using multi-material 3D printing and performed the comparison test. In experiment, the bottom plate is mounted on a sleeve bearing that enables the plate to rotate freely during compression. This is the force displacement curve given by the analytic model, and this is the finite element simulation result. This is the experimental measurement. We can see that our very simple analytic model can effectively predict the response of the unit cell structure. And these are the results for other geometric parameters. In each case, the analytical model works very well. Now, building on the analytical model, we investigate the deformation of the metamaterial system under external magnetic field. In this case, we need to account for the magnetic potential energy in addition to the previously mentioned mechanical potential energy shown here. Using the total potential energy, we can obtain the deformation of the metamaterial system for given magnetic field. Uh, Here the left panel is for the translational movement, and the right panel is for the rotational movement. H0 denotes the initial heat of the unit cell structure. We can see that for metamaterial system with relatively large heat, snap-through phenomenon can be observed when we gradually increase the intensity of the magnetic field. Okay, likewise, what we did in previous work, now we investigate the superimposed motion on the deformed system induced by magnetic field. This is the discrete equation of motion. Here, this term, the derivative of energy density function, is very complicated. Firstly, we use Taylor's expansion to simplify the equation of motion. After simplification, these two equations are still highly coupled. To this end, we introduced the reduced one degree of freedom model by establishing a linearized relationship between the translational and the rotational movement. This is finally obtained equation of motion, and we built the continuum model corresponding to the discrete equation of motion. The KdV equation has a solitary solution depending on the coefficient C eta 1, eta 2, and eta 3. To examine the continuum model, we solve the initial discrete equation of motion directly using numerical tool, and the analytical predicted solitary solution is applied as excitation to the system. As shown here, our analytical predictions agree very well with the numerical simulation. In the bottom panel, we examine the relationship we used, the linearized relationship we used in building our continuum model. The colored dots are extracted directly from numerical simulation. As can be seen here, all these dots are distributed near the dashed line that corresponding to the linearized relationship between the translational and the rotational movement. And this demonstrates that the relationship we used in building our continuum model is reasonable. Okay, please refer to our published papers for more details. And lastly, we want to acknowledge the support from European Research Council as well as the Mercury Action.